So we can now start. So welcome everyone to this second half of today's session of this workshop on New Horizons in Dispersive Hydrodynamics. So it's a big pleasure to introduce the first speaker today, Boris Konopelchenko from the University of Salento. So Boris was my PhD supervisor and is the person who introduced me to the theory of integrable systems and basically threw me in the Dragon's Den. So I'm very particularly pleased to introduce him today, and he will tell us about the universality of homogeneous Euler equation. So Boris, thanks for joining. The stage is yours.
Okay, thank you. Thank you, Antonio. You was really one of my best PhD students in all my life. Okay, and you see it easily. Well, okay, so I would like also to thank organizers for the kind invitation to this workshop, conference, opportunity to give a talk. And second, my congratulations to organizers for the excellent job they already did and continue to do. I'll speak about try to talk about some particular or probably remarkable property of so-called homogeneous Euler equation. We will see what is it. It is a joint work with Giovanni Artensi, present here from Bicocca University, Milan, and all technical details can be found in the article published in Journal of Physics A. I intentionally will try to avoid all complicated formulas because we are almost at the end of this long workshop, and probably a simple presentation without sophisticated mathematics it will be appreciated. In my case, the most complicated mathematical tool I will use will be the partial differential equations. Okay, homogeneous Euler equation presented here, and there is zero on the right-hand side. If you add here all terms, including pressure, viscosity, dissipation, type of dissipations, dispersions, it will be just famous Navier-Stokes equation, which is one of the basic equations of theory of continuous media. Even without these all terms, which may happen when we are able to neglect effects of viscosity, different types of dissipation, dispersion, and with constant pressure, we will end up with the following system of equations. Even in this most simplified form is very important equation which is used in many branches of physics, from hydrodynamics to cosmology. Well, this system of equation belongs to the class of system with quasi-linear PDEs, and in the recent decades, several advanced methods have been developed to analyze this type of equations. I will mention some of them. First, as quasi-classical limit of inverse scattering transform, and there are some names here. Then various algebraic geometrical approaches to address this problem. Some names we can see here. Methods of hydrodynamical reductions, some names you can find there, and several others. I'm sorry if I didn't mention somebody, but I would like to convince you and try to show that if you would like to deal with this system of equation, old style generalized Hadograph method is most appropriate tool to solve this type, to study and analyze different property of this equation. Okay, I did again something wrong. Okay, well, in fact, I will try to discuss a little bit more general form of this equation where alpha and betas are constants, lambda k are arbitrary functions. Of course, this constant can be removed away easily, obviously, except the cases when some of them are equal to zero. And this will be exactly the cases I will be interested in. This system of equations has a number of remarkable properties, easy to discover. There are infinite hierarchy of equations, which commute with that with different functions, lambda k. There is simple transformation from this system of equation to the original homogeneous Euler equation by the following step, and many other properties. And homogeneous Euler equation can be studied from other authors in a way when they considered reduction where the number of dependent variables is less than n. In my talk, I will try to discuss the cases when number of independent variables is less than n. So this reduction for low dimensional cases. And I will present here the basic results. First observation is that there are several important hydrodynamic type systems among this type of reductions for various n. Subclass of solution of this system provide us with a solution of that reduced system. And moreover, one can incorporate in certain way sort of dissipative and dispersion effects with the reductions of this equation to Burgers and Korteweg of this equation. Okay. Well, first, oh, I missed the page. I'm sorry. I'm sorry. Just to introduce. So in one-dimensional limit case, homogeneous Euler equation is just very simple equation. It has many names: Riemann, Hope, Burgers, Hope, and this is the classical textbook example of application of a method of characteristics. Category equation for this is equation of the following form, or in that form, exchange of variables. Anyway, general solution of this equation can be written in such implicit form, where you use 0 initial value of the function u for t equals 0. Extension of this type of category equation for the n-dimensional case has been done by Firely 1993, and that can be used in other papers. And the corresponding category equation is just an example of this equation, where I run from 1 to n with an fi arbitrary functions. Equation of characteristics very simple. General solution can be written in such a form. Oh, I'm sorry. So it should be u, not y, I. In different form, in that form where x are variables, Euler variables, and q are Lagrangian coordinates, it has been used even earlier by Zildovich and then Shaldani Zildovich in their discussion of the large-scale structure of a universe. So this representation for n-dimensional homogeneous Euler equation is very well known, and several results has been obtained. Okay, now I will go back to the page 4. For our generalized homogeneous Euler equation, we have the following category equations where fi arbitrary functions. Differentiated this equation with respect to x, k, and t, we obtain the following relation where matrix A has the following elements. Okay, written like that. And I can write it in terms of derivative of G L with respect to K. And now here, of course, we assume the determinant of A is different from 0. Otherwise, this formula has no sense. If we now combine these relations, we will see easily that U, which is solution of this system due to these relations, is a solution of our generalized Euler equation. In case when determinant A is different from 0, clearly determinant A equal to 0 correspond to the blow up of derivatives. In this case, which correspond to gradient catastrophe for homogeneous Euler equation, will be discussed in the talk of Giovanni Artensi. Matrix A, which we introduce, in fact, rather important. It is easy to see that obeys the following linear equation where dt is an own derivative and capital E is just identity matrix. If we introduce inverse matrix, the sign minus sign, we will get the following matrix Riccati equation. In fact, in such a form, equation, holograph equation for homogeneous equation has been used in paper of Evgeny Zakharov before in their discussion of the gradient catastrophe of Euler equation. I would like to also to mention the matrix A in fact is Jacobian of the following functions of that type. But we should remember that all our calculations are valid on the so-called mass shell, where all these functions are 0, and we should solve it with respect to U. Well, now let's consider the simple reductions. The simplest one is the matrix when the matrix A is diagonal, so the following relations are satisfied. There are two simplest cases. let's assume that all constant alpha and beta are equal to 1. Let's assume both these terms are separately equal to 0. One can easily see from the previous formula that implies that this type of derivatives, cross derivatives, are equal to 0. And in this occasion, n-dimensional Euler equation decouple in n one-dimensional Burgers equations with a single variable t and x1, x2, x3, and so on. It's rather trivial. Less trivial reduction in this with the diagonal matrix correspond to the reduction to the one-dimensional subspace. For instance, when x1 equal to x2, xn, let's call it x. So all these Gadogol equations are the following form. From differentiate with respect to x and t, we easily obtain the formula, and then one can easily see, take a look on that, that UL obeys the following set of n equations. This is just 1x, 1t, and one can see easily that is just nothing but equation in terms of Riemann invariance UL with characteristic velocity lambda n. Moreover, from this formula, one can observe that t given here, and with such a t, this type of constraint takes the following form. One can easily recognize in this formula and in that one the standard classical formula of so-called Salento generalized cartograph method, introduced them 30 years ago to analyze hydrodynamical type equation in 1 + 1 dimensions in terms of Riemann elements, but with n components. So this is just one reduction of homogeneous Euler equation. In other words, solutions of the homogeneous Euler equation, which correspond to the function FL obeying such a constraint, reduced to one-dimensional case as solutions of this system of equations. Or one can say it in a different way also. Now, less trivial or more complicated reductions to the n- dimensional case. Let's consider the reduction of n-dimensional space to n-1. For instance, chosen a way if xn equal to 0 and lambda k equal to uk. Or equivalent, one can put alpha n equal to 0. It's rather convenient. For that reason, this constant has been introduced. In this case, one can show that all components of u do not depend on a variable xn, and then we'll have the following relation. System of equation of homogeneous Euler equation is reduced to the following n equations. We have these elements of matrix A-1. And then if we impose the following constraints, this system of equation assumes the following form, where V is in fact 1/2 UN squared. And this is in fact an n-1 dimensional generalization of Jordan system introduced for the first time for n equal to by Kadama, myself, in this paper. And this system looks pretty strange. In fact, has a physical meaning describing adiabatic isoenthalpic motion of is a constant temperature. Indeed, okay, in this case, if we will consider the motion, adiabatic flow of the fluid, then we have the following system equation where the rho is density, p is the pressure, s is the entropy. And if we, in addition, impose, consider the isoenthalpy process such that due to this relation where W is constant, this expression can be written as the following way. Then we immediately observe that this system equation takes the following form. It is exactly our generalized Jordan system for n equal 4. So this reduction gives us this equation with a physical meaning. In other words, if we start from homogeneous Euler equation, we perform the following as a constraint from the previous slide, we get a solution of the equation which describes the adiabatic isoenthalpic motion at the constant temperature. Okay, next example. Now, of course, we would like to analyze the constraint we impose. Due to these relations, one can see that our constraints are equivalent to the following constraints of matrix A. Matrix A is a combination, is Wronskian Jacobian of the function FA. So all these constraints, in fact, are differential equations for these functions. Is there a different ways to analyze them? Okay, I will just present simple example to understand how things going on. When n equal to simplest case, category equation are the following two equations with f1, f2 to arbitrary function. Matrix A is of the following form. Elements of invariant matrices are given here. So this constraint assumes the following form, which implies immediately that fi, in fact, the components of the gradients of some certain function w tilde, which obey the following constraints also. At the end, we can see that our Hyderabad equation assumes the form of the equation of a critical point for the function w of the following form, where w tilde is the previous one. And the function w tilde obeys the following heat equation. And it's exactly the equation and condition which were obtained by Kandab and myself. For n equals 3, we have the following system of equations. Matrix A is more complicated. Constraints of the function f are a little more complicated again, but it is 3 equations. First order equation, differential equation for the function fi, if you use also that one. This is invariable system, rather complicated. But there exists one very simple subclass of solutions where function fi are components of gradient of certain function. In this case, it should be w tilde, I'm sorry. And one can see that Hyderabad equation again assumes the form of a question of for critical points for certain function of the following form, and constraint for this function are given by the following determinant equation, where the matrix B is given here, 2 by 2 matrix. Okay, moreover, in this case, one can show that matrix A is given by this second order derivatives of function W. This immediately implies the formal relation between the common derivatives of function U, which means that U, in effect, components of gradient of certain function phi. And our equation takes the following form. For n equal to, in general, okay, a system of equations rather complicated, but again, one can easily see the very simple solution of that form, where Hyderabad equation assumes this form, and with the function w of the following form, and defining equation again has the formula determinant of matrix B equal to 0, where matrix B is n minus have order n minus 1 of the following form. Again, one can see that in this case, due to these relations, U, in fact, is a gradient of certain function, and our equations, which we obtain, assume the following form. Okay, the first equation is very well known in the hydrodynamics. It appears in textbooks. Landau Riemann, for instance, is discussing isoentropic potential motion. But in our case, we have the system of 2 equations, so sort of Hamiltonian-Jacobi equation with potential V, which obeys the additional constraint, so-called self-consistent constraint. Again, rather would be interesting to understand what does it mean from the point of classical mechanics. For the case m equal 2, in fact, this equation is eliminating V, assumes the following form of conservation law. Well, another reduction. Now, for the schemes of the page 7, let's assume that we have the following constraints. And one can see that now a system or generalized of homogeneous Euler equation assumes the following form. And this equation again has application in physics. For A minus 1 is just shallow water equation in n minus 1 dimension. For arbitrary n, the system equation describes the polytropic motion with the following pressure P, where ρ is the density equal to Un. Again, I mean, sort of from the textbooks. Constraints for the matrix are more complicated. Again, one can show there is particular solution of these constraints, where FL are gradients of the function W, and this function W, a function WT, the W obey some constraints of the following form, and Hyderabad equation assumes the form of the equation for the critical points of the function W. Okay, in the simplest case, n equal 2, the function W of the following form, corresponding equation assumes the following form as a second order equation. And in fact, for a equal minus 1, one can find this similar equation in the books of Landau-Lifshitz. This system of equation, which was written before for two unknown, is diagonalizable, assumes the following form, where the Riemann invariants gamma plus minus are given here and characteristic velocity presented here. You can find this result, for instance, in the book of Wisdom. And this equation assumes the following form. This is just classical Euler-Poisson-Darboux equation, which has been discussed at different occasions for equal minus 1 in the paper of Martinez, Alonso, and Medina, and myself in discussion of the connection between the dispersional integrable system and the Euler-Poisson-Darboux equation. Okay, one can continue this type of discussion. Now I would like to present some more simple reduction of the three-dimensional homogeneous Euler equation. Let's consider the reduction to two-dimensional space given by x1, x2, x2. Let's call it x, and x3 equal to y, and lambda k equal to some functions. Heidelberg equation assumes the following form. From this system of differentiating, we obtain the formula expression for derivatives, and one can easily see that under this constraint, the system Heidelberg homogeneous Euler equation assumes the following form. It can be seen as a sort of two-dimensional generalization of the classical equation in terms of Riemann invariance. So we will drop, as there is no dependence on y, there are no such terms, we end up with a system for three Riemann invariants U1, U2, and U3 in one dimensions, as it was presented before. Okay, one can continue. Corresponding equation for function g or f have a really represent system of three equations, integrable, and there are particular solutions. Another reduction corresponds to the choice lambda k equal to uk, alpha 2, alpha 3 equal to 0, and beta 3 equal to 0. In this case, and it's simple definition of function f2, we have the following Heidelberg equation. Due to these relations, we end up with the following system of equations. What is it? And in fact, under the following constraint, we end up with the following three equations. And this is exactly the three-component Jordan system introduced by Kadam and myself some time ago. Equation for which give rise to solutions are presented here. Particular solution again is given by the case where the function g components of gradients, the function w obeys the following two equations, and the corresponding Heidelberg equation are the following equation for the critical points for function w. This construction given for n equals 3 can be easily extended for n component case. So let's consider n-dimensional general homogeneous Euler equation with alpha 1 equal 1, rest of alpha equal to 0, beta 1, beta 2 equal 1, and other betas are equal to 0. Okay? This corresponds to one-dimensional reduction. The Heidelberg equation assumes the following form, system of, in fact, n equations. One can easily show the following relations, and one gets the following equation for function UA. If we impose now these constraints, we end up with the following system of equations, of n equations, which is no more nor less this n-component Jordan system considered in this paper. This system has been introduced as the example of the parabolic quasi-linear system, integrable in the same way as the classical standard hyperbolic or elliptic interval quasi-linear or dispersional systems. Okay, these are simple examples, and there is a simple solution of that again, which corresponds to the particular choice of function g, I, f, I, where function w obeys the following constraint. Okay, I'm just going pretty fast because my time is go off. And the corresponding Heidelberg equation assumes the following form of the equation for the critical points for certain function w obeying certain equations. For finite n, Of course, in the formal limit, n goes into infinity. We end up with an infinite set of equations, which can be called the Jordan chain, given here. Not a finite set of equations, infinite. Okay, in fact, it has been in our paper appeared here, but then in fact, it was in different ways, has been presented in the paper of Martinez, Alonso, and Shabat, and also in the paper of Maxim Pavlov in different contexts. Nevertheless, again, if we formally extend our homogeneous Euler equation to infinite dimension, we end up easily with the following chain. And moreover, as one can see, a repeating discussion given before, solution of this Jordan chain, in fact, some particular subclass of solution of homogeneous, infinite dimensional homogeneous Euler equation. So if in all, because also one can add the choice of the function fi corresponds to the choice of initial data. Particular choice of function fi corresponds to particular initial data. For particular subclass of initial data, solution of homogeneous Euler equation, infinite dimensional, behave exactly as a solution of this Jordan chain, as in the previous examples. And now, the last point, I would like to mention some connection with the dispersion, which is the basic topic of this workshop. All the previous construction is just, one can say, quasi-linear, dispersionless, if we would like to say in such words. But in fact, this Jordan chain or particular reduction of the homogeneous Euler equation contains, as a particular cases, I will try to show equation which describe effects of dissipation and dispersion. Indeed, let's take this Jordan chain from the previous slide given. This first equation includes U1 and U2 and other equations. And now impose the following constraints that U2 is equal to the derivative of U1 with respect to X. The rest of the Jordan chain, infinite set of equations, produce no other constraints for function U1. Just definition of U3, U4, and so on and so forth. The first equation from this system, one can easily see, becomes the Burgers equation. So this means that under this constraint, Jordan chain and somehow the homogeneous Euler equation is reduced to the Burgers equation. One can put some parameter here, okay, doesn't matter. Well, what type of constraint we have due to this constraint? One can easily see this just appears one additional constraint for the matrix A, inverse matrix A. Remember that matrix A has components in terms of the first order derivatives. So this sort of differential equation for function f L of the second order, plus those also for the Jordan chain. If we consider restrict our initial data in such a way that will obey this constraint and those for the Jordan chain presented before, so this solution provides us with a solution of the Burgers equation and apparently describes the effects of dissipation in such a simple form. Okay, next step. Now let's impose the following constraint. And from the Jordan chain, we will not have other constraints. The first equation in Jordan chain takes the form of Korteweg Vries equation. The corresponding constraints for matrix A, just write this constraint in terms of A, because we know we have expressions of U1, U2 in terms of matrix A, elements of A minus 1. We obtain the following constraint. This, in fact, the PDs of the third order for the function Fl. So, solution of infinite dimensional homogeneous Euler equation, which obeys the following constraint, give us solution of Korteweg this equation. And now this is just connection with the main topic of this workshop with the dispersion. Okay, so what has been shown in these cases? If we will start with the homogeneous Euler equation, forget about no dispersion no dissipation, no viscosity, nothing. And if we formally extend it to infinite dimensions, this system equation is a particular version contains Burgers equation and Korteweg equation. And in particular, their solution constructed due to the solutions of the corresponding hydraulic equation with certain constraints. As this can be easily extended to the hierarchy, Burgers hierarchy, Korteweg hierarchy, and several other equations with different higher order derivatives and so on and so forth. Of course, generally speaking, or philosophically speaking, observations that one can construct solutions of the lower dimensional equation with higher order derivatives embedding them in the multidimensional equation, which are of the first order differential equation. All the idea, nothing new, nothing very special, except probably the point that in this case, we are dealing with a very important physically and mathematical equation. That is the homogeneous Euler equation in dimension n. Of course, there are a number of problem equations around all that, and all that is a process of study. Okay, thank you for your attention.
Thank you very much. Thanks, Boris. So we can open to questions. We have some time for questions. Is there any? So I think we have a question. A question from Sergei Gavriluk. So Alexander Chupakin, a pupil of Lev Ovsyannikov, studied homogeneous Euler equation by using a photograph type method. In particular, he also studied matrix Riccati equation. I wonder if you are familiar with these results.
Yes, thank you for these questions. Okay, when I wrote this equation for you, I learned it from the paper of Evgeny Kuznetsov. And then he gave me reference to this paper of matrix Riccati equation. Okay, of course, I would like to add there is a good probability that everything I presented today is written somewhere a long time ago, century ago, and hidden in some old books on hydrodynamics or quasi-linear equation. There is a good probability. But exactly this paper of Chupakin and his co-authors, they were just trying to solve this matrix equation in different occasions. I have these two papers. And they didn't discuss, in fact, the reduction to lower dimensions, which was the main topic of my talk. Kuznetsov then used this equation, in fact, matrix Riccati equation in trying to analyze the blow-ups of the solutions of earlier equation. But this will be exactly the topic of the Giovanni Arten's talk.
Okay, thanks, Boris. Any more questions? Actually got a quick one. So, Boris, what do you know about the properties of the initial conditions fulfilling this constraint on the matrix A? For example, are they bounded initial conditions in that satisfy?
No, for homogeneous Euler equation, function FL are arbitrary functions.
No, in the case where you reduce to the KDB or the Burgers.
Oh, okay. This is a very good question. Exactly belong to the last line written as questions and problems. In fact, it seems for me a quite reasonable question. What subclass of solutions of KDV, for instance, can be obtained in such a way? Very good question. I have no answer at the moment.
Okay, thanks, Boris. And any more questions? So if not, I'll thank Boris again, and we can move on to the next speaker.
Thank you.
Thank you, Boris.